You're welcome.
Okay, guys. So, the last chapter, it had like a variety of stuff in it. It was a variety of stuff that was a good amount of review. So let's talk about where some of that stuff would come into calculus. A lot of those problems, especially the real hard ones that were like inequalities and stuff, if we were in calculus and we had a problem where something like that was in it, just about every time I would use the calculator to do it. We'd graph it and do it that way. So we wouldn't rely on some of those techniques. You just needed to be exposed to those techniques in case you were ever called upon to use them. So in calculus, AP calculus, that would rarely happen. This section and this chapter in general is pretty key to AP calculus, especially this very first assignment. So big time important. It's not a hard section, but hugely important. We're using it right now in AP Calc. Right now we're using it, okay? So it's not nearly as difficult, I think, as those last couple sections were in a lot of ways. It's very important. So section 3.1 is all about different types of functional behaviors. And just how to look at functions, how to work with them. So let's redefine what a function is. So a function consists of what? It consists of several things. It's got a set of inputs and a set of outputs. What is that set of inputs called? It's the x's usually, but what do we call that? It starts with a D. The domain. Bless you. So everything that you can possibly put into a function is the domain. Everything that comes out of the function, everything the function hits, that's the range. So we've of course seen these before. They're going to become more and more important though. And they're not hard to work with. Domain and range. Range is hard sometimes, but these aren't big issues. They're not bad to work with, okay? A function also has a rule, of course. That's what we think of when we say the equation. When I say the equation of a function, I'm speaking incorrectly. A function is not an equation. An equation has something equal to something else. A function has a rule. It's a rule by which each input determines or computes how many outputs? Just one. So it's a unique output. If you put one thing into a function and two things come out, it's not a function. Some equations do that, but they're not functions. So you can't apply anything you know about functions to them. So let's write that real fast. Not every equation is a function. So what are some ways that we determine, that you learn to determine whether it was a function or not? If you have something like a circle, there's an equation for a circle. It's like x squared plus y squared. If this is a radius of 3, it's equals 9. Is that a function? If I put one x value in, like this x value, I hit there a y, and there's another y. The output is not unique in that case. So if you can visualize whatever your curve looks like, you can tell immediately if it's a function using the what? Vertical line test. So I can use the vertical line test if I have a graph to check if something's a function. So vertical line test. If a vertical line crosses the curve twice, or let's put more than once. Could cross more than twice. More than once, it's not a function, because then that output is not unique. Notice, just in that example that I put up there, you can just look at the equation and already guess that that's not a function. It's got y squared in it. Think about what's going to happen if you solve this equation for y. You get y squared equals 9 minus x squared. And then if you're going to square that, what happens? You have to use the square root. And when you use the square root, you always get plus or minus. So if you've got y to any even power, not x doesn't matter. If y is to any even power, you're going to have this plus or minus thing happen if you tried to solve for y. So you'd have more than one answer. So anytime you have y to an even power, is it a function?
No.
So let's write that down too. Y to an odd power is a different case. Y to even, never a function. Okay, so that's a quick check. If you see an equation, you can be like, oh, that's not a function. It's got a y to the fourth in it. It's got a y squared in it somewhere. It's not a function. Even if you don't have the picture.
Is that just at any point, or what?
I'm just saying, looking at the equation, if it says y squared, it's not a function. Vertical line test, you look at each points. Vertical line crosses it twice anywhere. That's not a function. But it depends. Do you have the picture? Do you have the equation? What do you have? Okay. So let's just practice function notation. Just on a couple examples. You guys should know how to do this, of course. So let's plug g equals 1 and g equals -3 in there. I don't think anyone really needs to see this, but just in case. So I plug 1 in. Remember, that's what the notation says. It means plug stuff in. So that's the square root of 9, which is 3. So if I plug 1 in, this is the way we want to think about functions. I put 1 in, 3 came out. I put -3 in. And 5 came out. If I put 0 in, what comes out?
0.
Square root of 7, right? Because that gets zeroed and you get square root of 7. So if you have 0, it equal root 7. So does what comes out have to be an integer? Does it have to be a fraction? No. Could be anything. Could be any real number, right? Let's see a new function. So we're going to talk about a library of functions that we need to learn over the course of this class. You guys have seen most of them already. So one of them is y equals mx plus b, a line. We know what lines are. Parabola is y equals x squared. We've looked at that a little bit. We're going to look at it a little bit more too. But we know that one fairly well. Another one that we saw last year in Algebra 2, and we'll come back to it, is the square root of x. You know what that looks like. By the end of the class, we're going to know what 1 over x looks like. You did see it in Algebra 2, though. Come back to that and look at that. This is all the functions we need to be able to picture. We need to know sine of x. We need to know cosine of x. And we need to know all the other trig functions. There's really not that many, though. There's like 10 or 15 functions, and that's it. So there's some of our library of functions. We'll add to it a little bit as we go. Here's a new one that we're learning today. This one's a rarer one, but it might come up once in a while. This is called the greatest integer function. So we have not seen this before. So let's look at what the picture of this looks like. The book does not show you what the picture of this looks like yet. I'm just going to go ahead and show you the picture. Okay? So here's what the greatest integer function looks like. It's like it's a sequence of pieces.
just continuous.
Yeah, and it just continues. So how do you get this kind of a function? This is something that's used in computer science a lot. So here's the definition. When I say greatest integer of x, that means the greatest integer less than or equal to x. So if I plug in 0.5, what's the greatest integer less than or equal to a half? Less than or equal to 0. How about this?
Why can't we make it 25?
What's the greatest integer less than or equal to 2.7?
2.
2. We need to try a few before you see the pattern.
Does it have to be equal to a whole number?
Yeah, so let's think about this. Let's do one more. Let me see what I tried. I did negative 1.73. What's the greatest integer less than or equal to negative 1.73? Negative 2. So it's kind of like you go down one each time, to the nearest closest integer, but you're going down each time. So careful though. What's the greatest integer less than or equal to, let's just do 1. Greatest integer less than or equal to 1. So do we see why the graph looks like this? And you said,
It has to be a whole number. So the only things that would count would be the ones that are.
right, so that's why we only get whole numbers and we have little chunks. What about the endpoints on each one of these? At 1, we got 1. So at 1,
at the bottom, open at top.
exactly. You guys hear Nick?
It's closed at the bottom over.
Because at 1, you're 1, not 0. So at 2, what's the greatest integer less than or equal to 2?
2.
So filled in? Nope. What about at 0? What's the greatest integer less than or equal to 0? Etc. And I could keep going.
Is this something?
Okay.
Is that the graph every time?
Yeah,
That's it?
unless you shifted it and transformed it.
How would you
Well,
draw
we'll see that over the course of the class. Or it's not going to be here.
Okay.
Okay. So this function, all you're going to do with it in this section is just start to look at it just a little bit. Okay, it's not going to do much with it besides what we just saw. So that's a different function. It is, I think, a tougher function. It doesn't come up a ton. Like in AP Calc, rarely it comes
So
up.
then are you gonna graph it like that?
You graph it. It's not going to tell you to graph it. It's not going to tell you to graph it.
Open source.
It means that there's not a point there.
Because it's continuous.
Yeah, it's in the next one. That's what
How is it hard to put together?
just have to be.
Well, you just said it's tough.
Well, some people say it's hard for them. So I can see that. Okay. So we're going to talk about a difference quotient. Okay, difference quotients are incredibly important in calculus. This is something that comes up quite often, and it's not hard. We need to practice it and get it down, so you might not get it down the first time, but after you've done it a few times with different functions, not a big deal. Okay.
Is that different or different?
It's difference quotient. So, what is the difference quotient? The difference quotient, we aren't going to understand what it's for yet. We're just going to be plugging in and using it for now, okay? And you'll see what it's for later on. So, this is what the difference quotient is. It's just this construction of function notation. It's like a combination of function notation. It's like 3 pieces, kind of. I like to think of it like that, and then it's not hard for me to do. So that is the difference quotient. So we're going to apply that difference quotient to this particular specific function and find out what the difference quotient for it is. Okay? So think of it as 3 pieces, and then you're going to put them together. You need to calculate f of x plus h, that's the hardest part. If it's hard, it's not. And then you subtract the function, and then you divide by h. What is h? We're just going to leave it as a constant for now. Just leave it alone. We'll talk about what it means in calculus if we take it with me. Someone else. Okay? So, I need to calculate f of x plus h. So let's just do that separately first. If you want to do this all in one shot, that's fine. I know many are going to be able to. So I'm plugging in x plus h for any x's. So it's going to be 3x plus h squared minus 2x plus h. Just plugged it in, that's all I'm doing. And then I simplify.
For your x value.
Then I simplify. So x plus h squared. Remember that's going to be x squared plus h squared. And what's that middle? 2xh. So if you need to FOIL it out, go ahead and do that or use the shortcut. And then I'll distribute here. Okay.
So do you have to put the? Why'd you put the h in all those? I guess.
Because I'm assembling this. It says plug in x plus h.
Okay.
I don't know what h is.
Alright, I see.
Just something we're plugging
So
in.
you're only doing the very first one.
Yep.
Okay.
Okay, so I get 3x squared plus 6xh plus 3h squared minus 2x minus 2h. Okay,
Simplify that bad boy. That can.
can any of those terms combine?
No.
What is that x squared plus 2?
So I did this separately. Now I'm going to put the pieces together. So this guy, for our function, is going to be that stuff. That's all f of x plus h. So you could just do this all in one shot, right?
So really, is it just gonna be 6hi?
There's going to be lots of stuff that simplifies, yes.
Plus 3h squared.
So this minus is this minus. F of x, I'm just going to grab that stuff and put f of x right here.
Half that stuff's just gonna go away.
It is. And it's all over h, right? It's just h. Okay, now, I hear people saying stuff's going to go away. They're right. When you distribute this minus, this just becomes
Negative 3x.
negative 3x and positive 2x. So now I see what cancels.
That and that.
Negative
Yep. So you did all that divided by h. I knew it.
Okay,
We can just get rid of the h on the 6xh.
Pretty much you're just getting rid of the fx.
Why'd you put that I?
Wait, where'd you put 6?
Where did you get the
Oh,
second 3x squared and 2x? No,
Hold
because
on.
from the second f of x.
Hey. I'm not done though. I can simplify this much further. Okay, what do these top terms all share?
Ax or h, yeah.
So I can pull it out. Okay,
So isn't it just 6x plus 3h?
Yeah.
Yeah.
Wow.
That's the first thing I've ever got.
so for our function, for 3x squared minus 2x, the difference quotient simplified to this, and then of course you can't simplify that any further. So in calculus, we would put something else in front of this, which we'll learn by the end of this class, and it would mean something big, like something quite
We don't want
substantial.
to learn
Okay.
Baby
You get to your
Baby steps.
Okay.
I get one quick.
Right. So
Let's get the assignment.
let's go talk about domain.
Yeah, no,
I understand that h, but we got fx plus h.
Like you. Like, did you get that?
I just don't understand where you got that second.
this.
I need
I was really jealous.
What was it?
I'm done. I
Okay,
want to
Bernie.
get after we finish that.
Pardon the interruption, Mike Dean.
Damn it, I thought it was gonna.
It's like, oh, sorry.
Okay, so we're gonna find domain. In this section, there's only 2 domain issues we need to worry about. By the end of the year, we'll have 4 total. And that's all you ever have to worry about. So let's look at a couple specific functions to see those 2 problems which could occur.
Do you ever excellence?
Nora.
Okay, so when I think of domain,
I think
you
it's.
guys with computers open, just shut them. When I think of domain, I think of what could break my function. So I need to think of what could I plug in to break this, to make it say undefined or something like that. 4. So let's think about in the abstract. What did I do here?
You made the bottom zero.
I made the bottom 0.
Which makes the whole
Okay.
thing zero.
So one of the 2 things that we need to know at this point is, if you have a fraction and you can make the bottom 0, that thing is not in the domain. So you set the bottom equal to 0. Doesn't matter what kind of equation it can be. It could be quadratic, it could be cubic, it could be anything. But if that bottom could be 0, then that thing is not in the domain. So we said 4 is not in the domain. So let's write out what the domain is. It's everything else except 4. So if we think on the number line, it's negative infinity to 4,
And then 4 to positive.
and then 4 to positive infinity. It's just there's like a hole at 4. If we want 2 pieces, we want to use OR. Thinking on the number line, here's 4, hole, all that other stuff. That's all in the domain. It's okay to plug in everything but 4.
It smells like we're a popcorn in here. I just wait out.
I just suspected. Why just 1? Because 4 is the one that counts.
Yeah, see, 3 is 3 over 0.
That's why you just
Oh,
just have to.
Okay,
There's a 4 in it.
one more thing, and then we'll stop there. This is the other thing we're going to worry about for now. If you have a radical, and it's an even-powered radical, like square root, 4th root, and even powered, then what could happen with this that would break it?
It'd be
It'd be
negative on the inside.
If the inside's negative, that's bad. So if we want the domain, the stuff we can put into it safely, we need to make sure that inside is positive.
We can't use any positive numbers. We have to use 0 or negative numbers.
The total inside.
For the specific one.
For this one.
So let's talk about this. Here's your strategy. You just need to take the inside and set it greater than 0 and solve that. So for us, the inside is this. So we just need to solve that inequality rather than guessing. You don't want to be trying to guess W's to plug in. That's going to be too difficult on many, many problems. You just want to set this up and solve it. So if you subtract 1,
W is less than or equal to
divided by a negative, so I switched. And then I think on the number line, what's that look like? So here's 0, so it's filled in this way. So my domain is negative infinity up to 1/3 bracket. If I tried to plug in anything bigger than 1/3, it's going to break that. If you plugged in 2, you're going to get an imaginary number, it's going to break. Plug in 3, it's going to break. Plug in 1, it's going to break. But if you plug in 0, you're going to be fine. If you plug in -1, you're going to be fine. Okay, so the strategy here is you take the inside and set it greater than or equal to 0, solve. So those are the 2 things. Inside of radical can't be negative, and the bottom of a fraction can't be 0. That's all we're going to worry about in this section. There's only 2 other things too that we'll learn. We'll pick those up later. All right, let's stop there. So there are some piecewise